I'm going to walk you through two example problems that will be similar to your big limiting reactant quiz. So hopefully this will be a useful resource in you preparing for that. And these slides are on Google Classroom with the two practice problems. So the first problem, you're provided a balanced chemical equation, and you're trying to figure out what the maximum amount of carbon dioxide gas that can be produced from 75.0 grams of iron 2 carbonate and 9.41 times 10 to the 22nd molecules of oxygen. So for this one, we have two separate starting amounts, and these are both reactants on the left side of our equation. So we need to set up two separate dimensional analysis setups in order to predict how much product we could make from each of those separately. So we'll put our 75.0 grams of FeCO3 in one setup, and separately we'll put our 9.41 times 10 to the 22nd molecules of O2. This will be requirement of you anytime you have two starting amounts. The only time you wouldn't do this is if the problem tells you what is in excess already, or it only gives you one starting amount, and so you don't need to do this for the two separate ones. All right, so for the top one, we're in mass. So the way we'll get from mass to moles, which again, moles is the only way we can use this balanced chemical equation to go from reactant to the product that we're interested in. So we'll find the conversion factor that has moles and grams in it, which is the one with our molar mass. So we'll need to find the molar mass of iron 2 carbonate from our periodic table. So iron has an atomic mass of 55.845. All right, and then carbon has a molar mass of 12.011, and oxygen has a molar mass of about 16, and there are three of them. So add all of those together, and you will get 115.856 grams, and that's how many grams are in 1 mole of that particular substance. All right, so the grams needs to go on the bottom, so it'll cancel out. So 115.856 grams of FeCO3 goes on the bottom, and opposite that is 1 mole. Whenever you use molar mass, 1 mole is always opposite of it. All right. Now we can convert from our reactant to whichever product we're interested in. Normally it doesn't matter which product you pick, both will give you the right, for whichever product you pick, you can figure out which one is the limiting reactant as long as you go to the same product. The only reason why I'm picking CO2 in this example is because that's what I'm looking for in the end of the problem, so it'll just save me time in the long run. So I'm going to go from moles of my iron 2 carbonate to moles of my CO2 using just the coefficients in my balanced chemical equation. All right, so there's 4 moles in my equation, and I'm going to 4 moles of CO2. Now, you technically can stop there, get to moles, whichever one would give you less as your limiting reactant, but since I'm trying to get this in liters at STP, I'm actually going to do that now. So I'm in moles of CO2, so now I need to find the conversion factor that gets me from moles to liters, and that is this bottom one. So 1 mole is 22.4 liters. So 1 mole of CO2 goes on the bottom, and 22.4 liters of CO2 goes on top. All right, so I multiply across the top, 75 times 1 times 4 times 22.4, and that all gets divided by 115.856, which is multiplied by 4, and I get 14.5 liters of CO2. I rounded it to 3 significant figures because I matched the 3 significant figures on my starting number. All right, same work, except now we're doing it for molecules of O2, so we'll need to use a different starting conversion in order to get it from molecules into moles. So I have molecules of CO2. That means on the bottom here, I need molecules of CO2, of O2 to cancel out. All right, so over here, remember molecules is just a particle. Particle is our general term to mean molecules, atoms, formula units, any of them. So for every 1 mole, there's 6.022 times 10 to the 23rd molecules. So 6.022 times 10 to the 23rd molecules goes on the bottom, and 1 mole goes on top. Now that I've finally gotten it to moles of O2, now I can use my balanced chemical equation. So the coefficient in front of the O2 is just a 1. So 1 mole of O2 goes on the bottom. And then the coefficient in front of the CO2 is 4. So 4 moles of CO2 goes on top. All right. And now last step, get it to liters of CO2 because that's what I'm looking for in my problem. So 1 mole of CO2 is 22.4 liters of CO2. Multiply everything across the top, divide by the product of everything on the bottom, and I get 14.0 liters of CO2. All right, so if you do this, and you're going to either liters, molecules, or grams of the product, your last step in both setups should be identical. That's how you'll know you're doing it right. If you were stopping at moles, then you'll have a different ratio there at the very end, but the top part will be matching. So notice how this whole section matches in both because we're going to the same product. All right, so the maximum amount of CO2 that can be produced is the smaller of these two numbers. All right, this would be the amount we make if we use up all of the O2. All right, and that's the smaller of the two amounts, so that's the maximum we can make. This is also called your theoretical yield. All right, so the limiting reactant is the reactant, so the thing on the left-hand side of the arrow, that made that smaller amount of your product. So for us, the limiting reactant is the O2, making the FeCO3 our excess reactant. All right, and then finally, we calculate the percent yield, and here we're given how much was actually produced, so that's our actual. So the percent yield equation is actual yield over theoretical yield times 100. All right, so we're going to do actual given in the problem divided by theoretical, which we calculated, all multiplied by 100. So for this problem, it is 91.4%. That's our yield. All right. So that's how you tackle one of these problems. I have one more example to show you, which will hopefully help in making sense of it's the next slide. So I'm going to erase this, and then we can start on that problem. Example number 2. Again, we're given a balanced chemical equation, and in this one we're being asked what is the maximum amount of our ammonium nitrate that we can produce in grams from 1.49 grams of HNO3, which is nitric acid, and 5.45 times 10 to the 21st atoms of zinc. All right, same exact process. We have to set up 2 separate dimensional analysis setups because we have 2 separate starting amounts. All right, so we have our 1.49 grams of HNO3, and separately we have our 5.45 times 10 to the 21st atoms of zinc. All right, so first one, we're in mass. The only way to get from mass to moles is to use our molar mass. So we'll find the molar mass of HNO3. So hydrogen is 1.008 from the periodic table. N is 14.007 from the periodic table. NO is 16, and there are 3 of them. Add all of those together, and you will get 63.015. Okay, so our 63.015 grams of HNO3 goes in the bottom, and our 1 mole of HNO3 goes on the top. Remember, whenever you find the molar mass, the number that goes opposite it is always 1 mole. It's the number of grams that are in 1 mole. All right, so we're in HNO3. So now we find the coefficient in front of HNO3 in our balanced chemical reaction. That's 10. So that's 10 moles of HNO3. And remember, in a normal limiting reactant problem, it doesn't matter which product you pick. I'm going to pick the one that I'm being asked about in this problem, so it's the ammonium nitrate. All right, and the coefficient that's in front of that is 1. I would still get the right limiting reactant if I had picked my zinc nitrate or if I had picked my water. I just wouldn't get the information I need, which is the mass of that. So this is my H4NO3. And now, in the end, the maximum amount of grams I'm producing. So now I need to go from moles to grams, all right, using this, but I need the molar mass of my ammonium nitrate. So for that one, I have N, which has an atomic mass of 14.007, and in my formula there are 2 of them, 1 and 2. H, which is 1.008, and in my formula there are 4 of them, and then O, which is 16.00, and in my formula there are 3 of them. Add all of those together, and I get 80.046 grams, which is equal to 1 mole of that particular substance. So now, since moles is on top, 1 mole of NH4NO3 will go on the bottom, and my 80.046 number will go on top. All right, so my grams cancel my grams of HNO3, my moles of HNO3 cancel my moles of HNO3, and then my moles of NH4NO3 cancel with my moles of NH4NO3. So I'm just the grams of the product. So I do that math, I get 0.189 grams of NH4NO3. All right, same exact process, except doing it for atoms of zinc. So atoms just falls under the umbrella of particles. So for the first step, I will need to use Avogadro's number to get those to cancel out. So 6.022 times 10 to the 23rd atoms of zinc are in 1 mole of zinc. Oops. All right. So atoms of zinc cross out. Now I'm in moles of zinc. So now I need to go to my equation to find the coefficient in front. So 4 moles of zinc are equal to 1 mole of NH4N3. That's what I'm looking for in this problem. The only requirement is that you always go to the same product in order to determine the limiting reactant. In one of these, I couldn't go to the ammonium nitrate, and in another one to the water, because then I wouldn't be comparing the same thing. So moles of zinc cross out, and now I need to use the molar mass to get to grams. 0.046 grams of NH4NO3 for every 1 mole of NH4NO3. All right. So if I wasn't looking for grams, I could have been going to molecules of this. If this was a gas, I could have been going to liters of this at STP, but for this particular problem, I was looking for grams, so that's what I converted it to. All right, multiply everything across the top, divide by the product of this times this times this, and you will get 0.181 grams of NH4 NO3. All right, so the maximum amount that I can produce of this product is the smaller of those two numbers. So 0.181 grams is smaller than 0.189. So that is my theoretical yield. All right, so my limiting reactant is the thing on the left that made that smaller amount of product. So for that, it's my zinc. That makes my excess reactant the HNO3. It is not always the top one's in excess, the bottom one's limiting. It just so happens in these two examples that that's the way the numbers worked out at the end. And then finally, the percent yield of the reaction. This is how much was produced, so this is my actual. My theoretical is what I calculated, so I always do actual over theoretical. So 0.146 divided by 0.181, all multiplied by 100. And in this example, that is 80.7%. Okay, so a lot of work, a lot of steps. That is the content of your quiz that you'll be taking on this. You will have one problem, and you will definitely be doing 2 separate setups, figuring out which one the limiting reactant is, and then calculating the percent yield at the end.